Quark matter under pressure. I'll first introduce quarks, and then quark matter, and the under pressure will follow. I was told that the theme of your physics presidential lectures this term is matter under pressure. I can't really connect to the first one, which was about the center of the Earth, but along the way, I'm actually going to set up the next two, the talks that will be 4 weeks from now and 8 weeks from now, which in their own way are also about quark matter under pressure. So what are quarks? I'm trusting that all of you have heard that matter is made of atoms, and atoms have nuclei in their middles, and nuclei are made of protons and neutrons, and those are made of quarks. But I want to say a little bit more about how we know these things. And starting more than 100 years ago, how do we know that atoms have nuclei in their middle? As of 1905, it was known they had electrons, but maybe the positive charge was in the form of some pudding. The way Rutherford learned that atoms have nuclei was to correctly interpret experiments in which you were shooting particles through a foil made of gold atoms. And if the positive charge was pudding, those alpha particles would have mostly gone almost straight through, but they didn't. Once in a while, they bounced off at large angles, and that's how Rutherford discovered nuclei. And this is one of the ways that we can see small things. It's one of the ways that we can see the microscopic structure in the early 1900s, the microscopic structure of what's inside an atom. And we'll come back to this theme of using a scattering experiment to see what's inside something twice more in the talk. By the 1930s, it was known that nuclei were made of protons and neutrons. By the 1960s, the question of what protons were made of was the question of the age. And it was a very confusing time if you were trying to answer this question in the 1960s. By that time, there were dozens of cousins of the proton that were known. I won't give you their names. They had various Greek letters naming them. Their charges could be +1 like the proton, or +2 or 0 or -1 or -2. And there was a Mendeleev-like understanding of how these charges, how the patterns of their charges could be explained as if they were made of quarks, which had fractional charges of 2/3 or -1/3. In a variety of ways, it was understood that you could understand the counting as if protons were made of these smaller objects. And the proton's cousins were as if either made of 3 quarks or 3 antiquarks or a quark and an antiquark. But only as if. I'm emphasizing the as if, because in the 1960s, nobody had ever succeeded in pulling a quark out of a proton and looking at it in isolation. And in fact, to this day, no one has ever been able to do that. So in 1968 to 70, Friedman, Kendall, and Taylor, and I should mention that I saw David Hogg this morning. He's not here this evening, but David was a student at MIT, and Henry Kendall was one of his professors, and David and I were talking about Henry. Friedman, Kendall, and Taylor decided to answer this question Rutherford style. They said, let's shoot a beam of stuff through the protons and see if the particles we shoot through it, do they bounce off at large angles? The particles were electrons in this case. This was not a popular idea in 1968, because if you shoot an electron at a proton, and if it bounces off at large angles, the proton is destroyed. It's blasted into smithereens. And what was thought at that time was, how can you possibly learn anything interesting about the proton by blasting it into smithereens? But Friedman, Kendall, and Taylor did this. Here was their target. The electron comes in from the left, and you look for the electron scattering with these devices, which are tens of meters in size. Here's a photograph of the actual apparatus with a person there. Rutherford's apparatus was about this size. So science had become bigger from the 1910s to 1968. And what they were doing in cartoon form, here's a proton, it's got some quarks inside. You shoot an electron off at large angle, and they had the clever idea, let's just focus on how likely is it that the electron comes off at a large angle. That's the question we'll ask. Yes, you blast it into smithereens. We won't try to understand that quite yet. And they succeeded. They saw quarks inside protons just as clearly as Rutherford saw nuclei inside atoms. This is, quarks are just as real as nuclei. You can see them in there. Quantitatively, the scattering at large angles is just as it was for Rutherford. But there's a sense in which this added to the confusion. Because if the quarks are real, you can see them in there. They're not just bookkeeping, they're real. I found them, I can see them. But why can't you isolate one all by itself? Clarity came in 1973 when Gross, Wilczek, and Politzer figured out the laws of nature that govern quarks. Those laws of nature are called QCD. I'm going to use QCD at various times. Those laws are the analog of the laws that Galileo, Newton, and Einstein worked out for gravity, or Coulomb and Feynman and many colleagues worked out for electricity and magnetism. So new in 1973, 52 years ago, this discovery of the correct fundamental laws governing quarks resolved all that confusion. And I'm going to tell you in a couple of slides how it resolved that confusion. But really, anytime you discover something fundamental for the first time, it opens new vistas. And this talk will be about the new vistas. And in fact, I'm going to come back to this point one more time. After we get a little farther in my story, there will be another moment when an amazing discovery opens new vistas. But first, how are the puzzles resolved? So quarks come along with gluons, just as electrons come along with photons. Photons are the particles of light. Gluons are their analog. Electrons have charge. They exchange photons. Photons are governed by Maxwell's equations. This is the physics of light and electrons. Quarks have charge. It's a new kind of charge. It was called color in the 1960s. Quarks are colored. They interact by exchanging these gluons. Gluons by themselves are governed by equations that look a lot like Maxwell's equations. There are many analogies between quarks and electrons, gluons and photons. But there's one little difference. The gluons themselves are colored, whereas photons are neutral. Photons have no charge. Gluons have this charge. Sounds like a technicality, but it's not. And Gross, Wilczek, and Politzer realized that this has consequences. They showed that as a consequence of this technical difference, the force law is different. And in particular, the force between quarks does not just go like 1 over r squared, the way electromagnetism does or gravity does. If you put quarks closer and closer together, the force grows more slowly than 1 over r squared. And if you pull quarks farther and farther apart, the force falls off less than 1 over r squared. And in fact, these laws of nature have a scale hidden in them, a scale capital R. And if you ever pull two quarks farther apart than capital R, the force between them stops dropping off. It's like you have a rubber band connecting them. And what is this capital R? Well, it's 10 to the minus 15 meters. And what is that? That's the size of a proton. So hidden in these laws is a scale, and that scale is not only the size of the proton, but all those cousins have the same size, and that is immediately explained by these laws. So what happens when you take a proton and kick one of the quarks really hard, which is what Friedman, Kendall, and Taylor had done? You kick this quark really hard, and you're optimistic. I'm going to pull it out and study it in isolation. But it is as if it's connected to the debris of the proton by a rubber band. As it comes shooting out, that rubber band shatters into bits of rubber, and those bits of rubber are not isolated quarks, they are cousins of the proton. And all of this is described in a quantitative way by these new laws of nature of 1973. And you can immediately understand why Friedman, Kendall, and Taylor were able to see quarks, because the quarks, when they're close to each other, or when you come very close to it as an electron and bounce off of it, they're weakly interacting. So if you can take a high-resolution photograph with a fast shutter speed and ask the question of where is one quark at one moment in time, that is like what Rutherford did for nuclei. But those same equations should describe the structure of the proton itself, and that turned out to be a much harder thing to calculate. It took 35 years to take the laws that were discovered in 1973 and calculate the mass of the proton, the mass of the rho meson, the mass of all of these cousins of the proton were all calculated quantitatively from the fundamental laws of nature for the first time 35 years after the fundamental laws were discovered. your speaker in 8 weeks is an expert on the methods of calculation that were used to do this, although she entered the field more recently than 2008. So this is not her work, but she is an expert on the kinds of methods that are used to calculate quantitative answers to important questions from these laws of nature. Her name is Fiala Shanahan. She'll be here 8 weeks from today. So, fundamental laws open new vistas. Already immediately in 1974, people realized, Collins and Perry were the first, that if you could somehow crush protons and neutrons on top of it, crush nuclei, you would make a soup of quarks. And in fact, you can go read their 1974 paper, and they called it quark soup. So, laws of nature 1973, quark soup 1974. But how on earth can you crush protons and neutrons on top of each other? The only way that they thought of at that time was to look in the center of a neutron star. Neutron stars are amazing objects. They have a mass that is roughly that of the sun, but their size is 10 kilometers, roughly that of Manhattan. Studying neutron stars is a very exciting area of scientific exploration. 4 weeks from today, Anna Watts will be here, and this is her area of expertise. I could say much more about neutron stars than I'm going to today, but Anna is speaking in 4 weeks. She will be speaking about neutron stars as an example of matter under pressure, and I will largely leave that to her. But in the last quarter of my talk, at the end today, I'm going to come back to cold quark soup in the centers of neutron stars. It's a beautiful example of quark matter under pressure. But I will leave that for the end. I want to spend most of the time today on hot quark soup. Already also, not quite 74, but by the mid-70s, through the work of many people, there's not a single key paper you can point to, but through the work of many people, it was known in the mid-70s that if you could find matter that was at 2 trillion degrees, not an easy ask, if you can find matter that's of 2 trillion degrees, that is such a high temperature that there would be so many quarks and antiquarks in the volume of a single proton that you wouldn't have protons. You would instead, it was thought, have a gas of quarks and gluons. This was named long before it was discovered in experiment. It was named quark-gluon plasma, QGP. And it was already understood in the 1970s that even if we don't know how to make it in the laboratory in the 1970s, it was understood that the Big Bang did it for us. When the universe was less than 10 microseconds old, temperature was more than 2 trillion degrees. And so all of a sudden, we have a chance to answer the question, where did matter come from? How did the first protons form? This is a very standard sort of icon of cosmology. The history of the universe runs left to right. I'm going to describe it right to left. Here's today's universe. At a time of about 1 billion years, that's when galaxies formed and structure formed. At a time of about 300,000 years, that's when atoms formed. Here at a time of 3 minutes, that's when nuclei formed. And we're going back to here. This is a time of 10 microseconds. This is when protons formed. So you can also talk about even earlier times in cosmology. You can talk about inflation way back here. But I'm going to be focusing on this time in cosmic history when the universe was 10 microseconds old. And hot quark soup fell apart into protons. So we have the laws of nature. Can we just calculate and answer questions from first principles? Yes, for some questions. We can reliably, this was already true in 2010, you can reliably, from first principles, from the fundamental laws of nature, calculate the pressure of hot quark soup. This time when the universe was 10 microseconds old and about 2 trillion degrees hot corresponds to about this pressure here. I'm going to use as a benchmark a pressure at the time when the universe was about 1 microsecond old, temperature 5 trillion degrees, which is about here on this plot, in a better unit, but I won't define a unit that I won't define. It sits right about here. So I can read the pressure off. When you read the pressure off, I know 4 weeks ago there was a person here who spoke about the center of the Earth. The pressure when the universe was 1 microsecond old was about 7 times 10 to the 24 times higher than the pressure at the center of the Earth. it was about 2.5 times 10 to the 31 times higher than the pressure of the Earth's atmosphere. If you would like a seminar series on matter under pressure, it's hard to beat this. The early universe wins. Now, you can then ask, well, so is it a gas? And you might make a mistake here by saying, well, suppose it was a perfect gas, an ideal gas. What would its pressure be at this temperature? The answer is this line here. And you might say, oh, this looks, probably it's pretty gas-like, because this actual pressure from calculation is not so different from that of an ideal gas. And that turned out to be wrong. Understanding what this stuff is actually like, is it a gas? Is it a liquid? Is it a solid? Turns out it's a liquid. Understanding that had to wait until it was reproduced in the laboratory. And in 1983, Veit Bucha and Fred Goldhaber calculated that you would need to do collisions at a certain energy that was about 100 times higher than what was available in the accelerators of 1983. If you wanted to reproduce the conditions of the Big Bang, make quark matter as opposed to protons and neutrons, that's what you needed to do. That's why the relativistic heavy ion collider was built on Long Island, a couple hours drive from here. And starting in the year 2000, these conditions have been recreated at RHIC. RHIC achieves collisions at 200 GeV above this criterion. And then more recently, since 2010, in Geneva, collisions at vastly higher energies have been reached. What these collisions do is they collide two nuclei, the things that Rutherford discovered. You collide two lead nuclei at such an enormously high energy that what you are doing is creating a little drop of stuff, which is 2 trillion degrees hot, 5 trillion degrees hot. In fact, 5 trillion degrees is roughly the right temperature for collisions at the Large Hadron Collider. That's why I used it as my benchmark. It's not a universe, okay? We're not recreating the entire universe. This is a diagram showing the history of the universe, but it's the stuff of the Big Bang. This is the same matter that filled the universe, but it's only a little drop, one nucleus in size. So it's 10 to the minus 14 meters in size. So you should think of these as little bangs. The universe was a big bang. When you have matter with pressure, such enormous pressure, and you make a little drop of it, what does it do? It explodes. And so these little bangs promptly explode very quickly. And here's such an explosion. So this is data from RHIC, the relativistic heavy ion collider, 2 hours drive from here. Two nuclei collided right there in the center of the picture. And this is about 1,000 particles coming out. This is the debris of the explosion. So we now become sort of forensic scientists trying to infer the properties of the thing that exploded from the debris of the explosion. The Large Hadron Collider at CERN is an accelerator whose circumference is larger than the length of an airport runway. In this tunnel under the Swiss and French countryside, you accelerate lead nuclei going one way and lead nuclei going the other way, and they collide here, 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 and here. When I go on sabbatical to CERN, my office is roughly here, and the house that I like to rent is sort of over here. There's the airport, to give you a sense of scale. When you look in the tunnel, you find an accelerator in which these nuclei are accelerated. And then you need cameras. I'll show you pictures of 2 of the cameras. There are 4. You need cameras to take pictures of the explosion. This is one of them. You can get a sense of the size of the camera, the detector, which I'm calling a camera, from the person in the cartoon. This is an actual photograph of that same detector. And this is 1 story. This is 2 stories. This is 3 stories to give you a sense of scale. This is another one of those cameras, and in this one, this is actually a little smaller than CMS. This one is called Elise, and there's a couple of people right there. These are enormously challenging experiments from the point of view of data flow rate also, because this is a typical picture, and you get 10 to the 9 of these pictures per second. So when a little drop of the Big Bang fluid explodes, this is what you see. This is what you see with photographs taken by the other cameras. And so these collisions really are making little droplets of the hot Big Bang, and what we see is their debris. So what can we learn? We got a big surprise in the early 2000s because people were expecting that gas. It was called a plasma. They were expecting a gas of quarks and gluons, and that's not what they found. They found a liquid. And so I want to explain how this liquid was found. How can you tell by looking at debris like this that what you have as a liquid? I'm going to try and explain that. So, but before, I'll just point out the irony. This is the opposite of Rutherford's surprise. Rutherford was looking for pudding and found point-like nuclei. Freeman, Kendall, and Taylor found point-like quarks. This surprise has the opposite character. People were looking for a gas and found a liquid. And it turns out that the liquid that we discovered in this way has less internal dissipation as it flows than any other known liquid except possibly one. The way you quantify how much internal dissipation there is when a liquid, say, flows around a curve is this dimensionless quantity. This is a dimensionless measure of the shear viscosity, for those of you who are familiar with shear viscosity. If you don't know what shear viscosity is, it doesn't matter. This is a parameter that measures how good a liquid you have. Smaller means better liquid. And the discovery that this quark soup is a liquid is actually what has made it interesting to the broader scientific community. Liquids are much more interesting than gases. So how is this discovery made? Not a la Rutherford. I'm going to tell you how this discovery was made by telling you how this discovery can be made with a different liquid. The one terrestrial fluid we know, which is almost as good a liquid as hot quark soup, is 10 to the minus 9 degrees instead of 10 to the plus 12 degrees. It's 21 orders of magnitude colder. Our colleagues in atomic physics know how to trap clouds of atoms. They know how to play games with the interactions between atoms to make the interactions very strong. And they can study, they don't call them explosions, but I will call them explosions. They can study explosions as follows. So this is a cloud of atoms, and it's literally a photograph of this cloud of atoms. And they have engineered a cloud of atoms which is cigar-shaped. And it's trapped in this shape, and then you turn off the trap. So the experimental physicists trapped it in this shape. Now I turn it off. Suppose this was a gas. Suppose you have a gas trapped in a shape like this. You turn off the trap. A gas is lots of atoms. They're all traveling in random directions. They're all going random directions. This will circularize. This is the actual set of photographs of the experiments. And you can see, just with your eye, that this gas expands with much greater force in this direction than in this direction. That's what you expect for a liquid. Because for a liquid, the way you analyze this is you say, oh, the pressure is highest in the middle, and it's the gradients of pressure that drive expansion, and the gradients are much greater this way than this way. So this should explode with greater force this way than this way, and that's what happens. So I'm training your eyes to see that when you see an asymmetric explosion like this, it has to be a liquid, not a gas. You then do a quantitative analysis. You don't just look at the pictures as I've done, and you extract this 8 over s parameter, and you find that this liquid has an 8 over s around 0.4, and we'll come back to that. So now I can show you how we know that hot quark matter is a liquid. These are actual explosions photographed at the LHC. This is not, however, the same as this kind of pictures, because what you see at the LHC is just the debris. You don't get to see a movie. This was a movie, early time, later. At the LHC or at RIC, all you see is how many particles fly out this way with what energy, how many particles fly out this way with what energy. And what you see is in this collision, a lot more particles flew out this way and this way. Fewer particles flew out this way and this way. That's only possible if what exploded was a liquid. And it's only possible if the droplet that exploded was not circular. But that's easy to get because when two lead nuclei collide off-center, they will make a blob of stuff which is not circular. At the overlap of two circles is an almond. So this is the explosion of an almond-shaped blob of Big Bang matter, blasting with more force this way than this way. And you can do this quantitatively. I won't today. And when you the work of thousands of scientists, experimental and theoretical, say between 2005 and 2015, showed that doing everything I just said, but quantitatively, this dimensionless measure of how good your liquid is between 0.1 and 0.2 for hot quark soup. For water, it's between 1 and 10. For the liquid of ultra-cold atoms, it's 0.4. This is the record as far as we know. So what this is telling us is that in hot quark soup, quarks and gluons are not free. It's not a gas. You should not think of it as quarks and gluons flying long distances like in a gas. They're always bumping into each other. You should think of it as quarks and gluons rattling around and continually bumping into each other. They're never not bumping into a neighbor. So the picture of this hot quark soup is that the quarks and gluons are not confined into protons, but they're also not free. So the expectation of the 1970s was half correct. They're not confined, but they're also not free. So you make a drop of this stuff with a pressure that's 2 times 10 to the 31 atmospheres. What does it do? Well, if your drop is the size of an entire universe, the Big Bang, it expands and cools, and it takes 10 microseconds to expand and cool. And when it's 10 microseconds old, it falls apart into a mist of protons. Those protons live on for 13 billion years and become us. If you make a little droplet of the stuff in the laboratory in Geneva or in Long Island with nothing around it, it explodes much more quickly, and the shape of the explosion tells you about its liquidness. And that's the great discovery that we made in the, say, period from, let's say, 2000 to 2015 from studying explosions like this. There's a lovely analogy between the Big Bang and the Little Bangs. This is the Big Bang. Many people here in this room study this data like this. What happens in the Big Bang is you have some lumpy initial state. The lumps are very interesting. They might tell us about inflation. Those lumps are processed hydrodynamically, and at the end, the debris of the explosion, the Big Bang, is these microwave background photons. You describe them quantitatively with a curve. The data are the black dots. The curve is a theory calculation. It works magnificently. To understand this theory calculation, you have to understand the properties of the cosmic fluid and the lumpiness in the initial state. Same here. These are little bangs. These are actually simulation, not data, because you can't take pictures of the initial state of a nucleus-nucleus collision, but they kind of look like this. These explode. They make debris. The data are the black dots. The theory curves are the colored lines. You can see it's not quite as perfect as in cosmology, but we get very good fits to large data sets. And from that, we learn something about the 8/s at RIC collisions or at the LHC collisions. This is a very good way of conceptually thinking about what we're doing. I will end this first half of the talk by quoting a former MIT colleague, Vicky Weisskopf. I had the privilege of meeting him very late in his life, long after he retired, but just after I arrived at MIT. In 1977, which is long before I met him, he was giving a talk at an after-dinner talk in honor of Edward Purcell, who had done great work on liquids. And Vicky wanted to pay attention. Vicky wanted to pay homage to Edward. He wanted to talk about how amazing Edward's work was, and he thought he would do so by describing how complicated liquids were, how amazing it is that Purcell has understood liquids. So here's the beginning of his, the write-up of his talk. This is the first paragraph of his write-up. Assume that a group of intelligent theoretical physicists had lived in closed buildings from birth such that they never saw the world. What would they be able to predict from a fundamental knowledge of quantum mechanics? So suppose you took theoretical physicists, gave them the laws of nature, locked them in a room, and said, what can you calculate? Here's what Vicky said. Those theoretical physicists would probably predict the existence of atoms, and of molecules, and of solids, and of metals, and of insulators, and of gases, but they would most likely not predict the existence of liquids. Vicky, 1977. What Vicky didn't know is that the experiment was being done. Okay? In 1973, all of the theoretical physicists on planet Earth were given the laws of nature that describe quarks and gluons. They didn't know that they had a deadline. The deadline was the year 2000 when the first experiments would be done. Between 1973 and 2000, nobody realized that these equations describe a liquid. It took the experiments which were done here on Long Island and then analyzed in collaboration with a lot of theoretical physicists to realize that hot quark soup was a liquid. So Vicky Weisskopf was correct. So that's the end of the first half of the talk. What next? You know, we have discovered the earliest liquid to exist, the hottest liquid to exist, the source of all of the protons in the universe. It's the most liquid that's ever existed. It is, in a sense, the simplest form of complex matter because it's very close to the fundamental degrees of freedom of the laws of nature. So are we done? As I said once before in this talk, anytime you make a great discovery, it opens new vistas. And same is true here. What are the new challenges that this discovery posed? So I will speak about two. Anytime you discover a new form of matter, you ask, what is its phase diagram? This will be the last 10 minutes of the talk. But first, I'm going to go to this challenge. How on earth can weakly coupled quarks and gluons, they're weakly coupled when they're close to each other, how can they conspire to form a liquid? Can we understand the microscopic dynamics of what's going on in this liquid? Can we probe the original liquid? How can we see its inner workings? Well, we want to do Rutherford. I would love to take a drop of this liquid to Stanford and do what Friedman, Kendall, and Taylor did. Shoot an electron beam at it and see its structure. The way you see how something is put together on the inside is you do a scattering experiment. That's how you see its inner structure. Can we do that? Well, no, you can't bring it to Stanford because this liquid explodes. It explodes in 10 to the minus 22 seconds. No time to bring it to Stanford. So we have to use a probe that's made in the same collision that makes the soup. And here we come back to this cartoon. Remember, when you clobbered a quark and sent it shooting off, it became this spray of smithereens. This is called a jet. But when you clobbered a quark, before it became this stuff you see in the end, at the very moment after you just hit it really hard, it was shooting with high speed to the right. We're going to look for collisions in which, in addition to making a blob of soup, we made two quarks that were going to the right and to the left to give us a picture like this. This is data from CMS again. So this is the explosion of a drop of that liquid. And this is a special event where the experimentalists in there with their camera discovered a blob of liquid and two of those sprays or jets back to back. So how did that happen? So this is data. This is obviously cartoon. So two nuclei collided into the board, out of the board. They made the blue blob of liquid. In the same collision, right there, a quark from one nucleus, like Rutherford, a quark from one nucleus scattered off a quark from another nucleus at large angles and made a bullet shooting this way and a bullet shooting this way. The bullets are quarks. So here we have a chance of doing the Rutherford experiment, except it's a lot more complicated than Rutherford because we don't have control. We don't get to engineer our particle beam. We have to take what nature gives us. And these jets are pretty complicated objects. They're much more complicated than electrons. They shower and branch. They look like this in the cartoon. They don't just look like an electron. But I have a probe here shooting through the plasma, through the liquid. I have a probe here shooting through the liquid. Can I see events where this quark in my probe scattered at 45 degrees? That would be Rutherford again. So this is one of the quests for the coming 2-3 years, and I'm going to set you up to understand how we can achieve this. We're quite close, actually, but not quite there yet. One of the challenges is when you shoot a bullet through liquid, it makes waves. So there's another set of rich and interesting physics which has to do with the blue stuff here. So you can ask, does one of these particles scatter at 45 degrees? You can also ask, what about the waves in the blue stuff? And all of that is hidden in here. This is what real data looks like. How can you tell that in this jet, there was one particle in the jet that scattered at 45 degrees? How can you tell? How can you tell that in this explosion, there were waves in the soup? This is the frontier today in this field. So the reason why we study jets is to study the structure of quark gluon plasma. The reason why we study jets in this context, there are other reasons in other contexts. Jets provide the best chance of doing a Rutherford experiment on quark gluon plasma, on this hot quark soup. I've got a droplet of the hot Big Bang matter. It only lives for 10 to the minus 22 seconds, but in that time, I want to do a Rutherford experiment. That's what jets are for in my world. But they also offer the best chance of watching how the droplet responds to the bullet. Can we see how the wake of the jet ripples in the liquid? It is not easy to decode the answers to these questions from data that looks like what I showed you a second ago. But to give you a sense that we have a chance, these are day one LHC data of a jet back-to-back with a jet. This one has energy 205 in these units. This one has energy 70. And it's not that energy conservation is violated. So this is at angle pi. This one is back-to-back with this one. It's not that energy conservation is violated. What's happened is that this jet lost a lot more energy, and that the lost energy is somehow distributed in the grass here. So day one at the LHC, you can see that jets are dramatically modified by their passage through the quark, through the hot quark soup. So there's a chance of learning something from these data, because you can immediately see that in an event like this jet is much less modified by its passage through the soup than this one. So we have a chance. What can we actually learn? Theorists now are important. This is the Flatiron is a center for theoretical physics. I'm a theoretical physicist. Theorists are really important in this context because it's not so obvious how to do this. I'm going to try to give you a sense of what theoretical physicists are contributing at this moment. I want to, there's actually two earlier steps that I'm not going to speak about today. I want to give you a brief sense about how we might look for the wake of a jet. And then I want to give you a brief sense about how we might look for Rutherford scattering off of hot quark soup. And I'm going to do this as a theorist, not by saying I will do a first principles calculation that answers all questions precisely, because nobody knows how to do that. These are very complex dynamical questions with a complex probe shooting through a hard to understand liquid. Nobody knows how to do these calculations from first principles, so we use models. And what are models good for? Models should not be seen as, I will use my model to describe the data precisely. That's actually not the goal, because your model has inadequacies. If you use an inadequate model and it describes the data precisely, what have you really learned? So what models are good for, in my view, is that you can do things in a model that you can't do in the real world that allow you to train your eyes. So in particular, I want to use a model to figure out what are the ways of looking for observables that are dominated by the wakes that the jets make in the soup, or insensitive to the wakes that the jets make in the soup. If I want to study those waves, I need this kind of observable. If I want to look for Rutherford scattering, I need this kind of observable. So one of the things you do at this stage in the history of this subject is you tell the experimentalists, measure this and measure this. This is how you look for the wake. This is how you look for Rutherford scattering. So I'll say a little bit more about the wake in a second. So the model that I'm going to use, I won't actually go through this slide. I did want to say that it's been developed by many people, including me, over a decade. And it is a hybrid model for describing jets in the soup. Hybrid because we use one language of theoretical physics to describe the jets, the theory of quarks and gluons from 1973, and a different language to describe the soup. We use hydrodynamics, and we use strongly coupled methods that I won't describe here. So it's like the blind men and the elephant. We use one language to describe one part of the elephant, another language to describe the other part of the elephant, but we don't have a way of describing the whole elephant yet. So in cartoon form, here's my blob of liquid. Here's my production of a quark going this way and that way. This quark going this way fragments into a jet. Every particle, so I describe this red dot, laws from 1973, laws from 1973, laws from 1973. So I describe this branching structure with QCD, the theory that we've known since 1973. But then I have to ask, how much energy does this quark lose as it's fighting its way through the soup? And I'm using a formula here, which I won't walk you through, but this formula comes from an understanding of strongly coupled physics. We don't have this formula for QCD. If someone knows how to calculate this formula for QCD, it would be a big advance. This is a model description. So we have a model for describing how each of these particles loses energy, and the lost energy doesn't disappear. It goes into the wake, which we can describe. And what we can do in the model is turn the wake off. This is impossible in nature. Turning the wake off means that you've just violated momentum conservation. All of these particles lost momentum. You cannot do this in an experiment. You can't turn off momentum conservation. Momentum is conserved. But in my model, I can have the wake on or the wake off. And I can look and see what predictions from the model change when I turn the wake off or on. I can do that in a model. No experimentalist could ever do that. And so at a conference that happened in Japan in September, so less than a year ago, major progress was reported on looking for the wakes of jets, the wakes in the little droplet of Big Bang matter that is produced in a heavy ion collision. If I were speaking to an audience of physicists in my own field, I would advertise my own contributions at this conference. I'm going to skip these two contributions. I have them in the backup. The one I'm going to pick for today was an experimental physicist, Yenji Li. His talk, I'm reporting new data from CMS. What did he report? So look, I've told you we want to see the wakes. This is what you would first imagine. This is something that we can do theoretically. I have a droplet of fluid. I have a bullet shooting through it. There are sound waves produced in the fluid. This is compression. This is rarefaction. These are sound waves. And you have a bullet going through a liquid. If I have a bullet shooting through the liquid behind the bullet will be dragged along. That's what this shows. This is momentum of the fluid in the upward direction, and there's a lot of upward momentum in the fluid right here because the bullet is right there, and it's pulled the liquid behind in the upward direction. If we could take pictures of like this in data, we'd be done, but in data, this is 10 to the minus 14 meters across. You cannot take a picture like this. This is going to explode on you. When this explodes, this, which looks so beautiful here, when it explodes, it's actually boring. When this explodes, it's just a few extra particles with no interesting structure. When this explodes, though, what does it mean that I have liquid pulled along this way? It'll mean I have more particles on this side and less particles on this side. And that's what Yenji Li took advantage of. So this is, again, this is model calculation from the model that I helped to develop. Less particles on this side, more particles on this side. So what Yenji decided to do was to look at events where there was a jet going that way and no jet this way. Instead, there's a Z boson going this way, and Z bosons don't see the fluid. So now, if you look on the Z boson side, there should be fewer particles because the bullet moved some fluid. You should see fewer particles near the Z. And that's what Yenji measured for the first time earlier this year. Blue is what you see for a jet back-to-back with a Z boson in proton-proton collisions where there's no soup. Add the soup, you see extra particles around the jet. and a depression, fewer particles back to back with the jet. This was never seen before this year. So this is an experimental discovery, but how did Yenji know what to look for? Well, we, with our model, had made predictions before he did the experiment, and so had the other people with models on this plot. Our model is the blue solid and the blue dashed. We had predicted before the measurements were made that in the real world, where there's a wake where jets make wakes, you should get this blue curve. That was our prediction. If you turn the wake off, dashed curve. And there's the data. So he knew what to look for because of the theory work we had done before. And the reason I'm telling this story with this example is that the measurement has now been made, and your eyes are trained by the theoretical modeling to say, aha, I've just seen the wake of a jet. Even though it's a very strange way to look for the wake of a jet, you would normally think, well, wake of a jet, I should look over here. The jet was over here. But actually, the most distinctive way of seeing that there's a wake of a jet over there is to look over here and see a depletion. And that's something that we theorists had pointed out and now has been seen. The other two examples from that conference are things that we theorists have been pointed out, and I hope the experimentalists see them next year. But I won't tell you the story now because I want to go on to Rutherford scattering. I'll just show Yenji's last slide. This is a bullet going through an apple. This is a bullet going through a drop of quark gluon plasma, and this is a duck going through a lake. They all make wakes. You can't see it, but the fluid behind the duck is following the duck. The fluid behind the jet is following the jet. And we now have unambiguous evidence for the wake created by a fast-moving quark. This is a significant experimental advance of the past few months. OK, now flip your goal around. I want to find observables that are for which the wake is invisible. I want to see through the wakes. I want to look just at the jet particles. Can I see a jet particle scattering by 45 degrees? So this is work. The theorists here are Zach Hulcher is a student at Stanford, Danny Pablos, who was a postdoc in Italy. He's actually now faculty in Spain. And I'll skip this. What you need to do is you first need to do a QCD calculation. I have a quark shooting in. You have to do the Rutherford calculation for a quark scattering off of a brick of soup. The metaphor is funny here, but this is the kind of theory calculation that we do know how to do, because there's no dynamics in the soup here. And so you can ask, what's the probability that you see a scattered quark with momentum p and angle between 0 and pi? It's calculable. And then we go back to our model and we say, let's treat this little bit of soup like a brick. Did this quark scatter? Nope. Did this scatter? Nope. Did this scatter? Nope. Not one scattered. So at every step here, you roll dice and ask, did the quark scatter? If it did, you put in the scattered particles. And what you see, this is obviously cartoon, what you see is that this jet, this spray of particles coming out, in this extremely unlikely event of seeing two scatterings, this will never happen, this jet has sprouted two new prongs. So the thing we're looking for is jets that sprout and one extra prong. And this is very directly the analog of what Rutherford saw. There was a scattering here like Rutherford, and this jet, its shape got modified. Instead of being a one-humped camel, this became a three-humped camel. We'll actually look for two-humped camels here. So this is angle. This is 45 degrees. 0.8 radians is 45 degrees. This is how much more likely is it to see a jet with two prongs in lead-lead collisions than proton-proton collisions. And 4 model calculations, only one of which is a prediction for the real world, because in the red one, we have the wake on and elastic scattering on. So this is Rutherford included, wake included. Turn off the wake, and you get green. So we've engineered an observable where whether the wake is on or the wake is off makes almost no difference. Turn off Rutherford scattering, and you get blue. Turn off both, you get black. So we have told the experimentalists, please measure this. And I could show you data which is almost this, not quite. This 150 is key. They've measured it with where that threshold is 100. It's not quite as good, and the error bars are big. They tell us that they'll be able to measure this with the sensitivity needed either in 2025, which is this year, or 2026, which is next year. So we are, I think, on the edge of seeing Rutherford scattering of quarks in a jet scattering off of the Big Bang soup, which is what this would be if there were data on this plot. So I haven't done this subject justice. I've given you a sense. There's actually about a dozen observables that people have proposed for experimentalists to measure. All of them have to do, they're in character all like this. They're about sprouting extra prongs on a jet, but the ways of doing it are different. But this is not an audience that is interested in the details of one observable versus another. There might be, like if Ken Van Tilburg were here, he'd be interested, but most of you, I think, will allow me to continue. This is the same slide I've shown 3 times already. I hope now I've convinced you that the next few years are going to be a golden age of heavy ion collision jet physics. There is a brand new detector in Brookhaven, which started taking data last year. Its main data taking run is this coming year. It was built to study jets. The LHC is in the middle of what is called run 3, and then run 4 is to come. These are higher and higher statistics to get more and more photographs of the kinds of rare events in which you have jets of the type that I'm talking about. So we theorists have been busy in advance of these measurements, making the kinds of advances that tell the experimentalists what to look for in order to learn about the microscopic structure of the soup and to see the dynamics of its ripples. So in the last 10 minutes, what about this other question? What is the phase diagram of this stuff? So here is a phase diagram from condensed matter physics, not the field I'm talking about at all. In a typical condensed matter physics talk, you have phase diagrams with temperature on one axis and doping on the other. Doping in condensed matter physics is having more electrons than holes in your crystal. And this is, in fact, a cartoon of the phase diagram for the cuprate high-temperature superconductors, where in this region you see high-temperature superconductivity. And here, this is actually their analog of quark-gluon plasma. Here is our phase diagram. Temperature on the vertical axis, doping on the horizontal axis. Doping for us is more quarks than antiquarks. So everything I've told you so far has been along this axis. The early universe started here, cooled like this. LHC heavy ion collisions start here, cool like this. Suppose you could study matter which is at these extreme conditions, but has a large excess of quarks over antiquarks instead of approximately equal numbers of quarks and antiquarks. There's a very interesting story here, which is a program that Brookhaven is playing a big role in, but I want to go to the extreme in the other direction. This is zero temperature, high density. This is what Collins and Perry wrote about in 1974. They said, take nuclei, which live here, crush them. Can you take nuclei, crush them to make cold quark soup out here? Cold quark soup turns out to be a superconductor in the same way that this is a superconductor, except here it's a superconductor because electrons pair. Here it's a superconductor because quarks pair. We know that from theoretical work done around the year 2000, sort of from 1997 to 2000 and plus. And what's new is that for the first time, this paper, which I'm very proud to be an author of, this is my graduate student, and this is a colleague in Norway. This paper, which is very recent, is the first empirical constraint on the properties of this stuff. And so I want to end by giving you a sense of how you learn something about cold quark soup. How can you squeeze matter so high density as to crush the protons into a soup of quarks without heating it up. If you go and collide nuclei at the LHC, you crush the protons, but you heat them up to an enormous temperature. The only way we know, we can't do this in the lab, but the only way we know that nature makes matter at enormously high densities and low temperatures is to build a neutron star. The heaviest known neutron stars are about twice the mass of the sun. They have a radius about that of Manhattan. And the weight of the star crushes the matter at its center to about 4 to 5 times the density of an atomic nucleus. And to a pressure, it's not quite as high a pressure as the pressures of the hot quark soup, but it's a respectable 10 to the 29 atmospheres. So this cold quark soup, possibly at the center of a neutron star, it doesn't explode. The reason it doesn't explode is it's held in by the weight of the star on top of it. And the way we learn about the properties, in particular the pressure of cold quark soup, is by combining things we know from old-fashioned nuclear physics for low-density matter, things we know from QCD for very high-density matter, and things we know from astrophysics of neutron stars coming from X-ray observations from a satellite on the space station called NICER, coming from gravitational wave observations when 2 neutron stars collide, and coming from radio astronomy measurements which tell us about neutron star masses and indirectly, well, you learn more about radii actually here. From all of these astrophysical sources, the best available knowledge about how the pressure of the matter inside of a neutron star depends on its energy density looks like this. What can we learn from this? I'll skip this and go to this one. The way I like to learn from this is to make a plot of the pressure that's analogous to the one that I used for hot quark soup before. Before I plotted P over T to the 4th versus T. This is the plot I had at the very beginning of the talk. The analog is this plot. And what you see is that this is neutrons. This is how it behaves. And then something changes and it flattens out. And this flattening out on this diagram is what quarks do. So, and the best empirical constraint on the equation of state today is this brown band. And what you see is that 1.4 solar mass neutron stars right there, they're neutrons all the way in. 2 solar mass neutron stars seem to possibly have a quark matter core because they're right where things are flattening out. And this green vertical band, which has a lot of uncertainty, represents the most massive possible neutron stars, and we don't know what that is, but it's probably something like 2.3 solar masses, but not known well. If you find a 2.3 solar mass neutron star, this is telling you that it will have a quark matter core. 2 solar mass neutron star likely has a quark matter core. That's the work of these authors. And so there's growing evidence that 2 solar mass neutron stars have cold quark soup in their cores. And then what we did was to flip this logic on its head. Instead of saying, how can we use all this to learn about the equation of state of matter, we're going to flip it around and say, given what we learned about the equation of state of matter, can we learn about the properties of the soup itself? And the central uncertainty in understanding color superconducting quark matter is what is the value of the gap. A lot of people, including me, did a lot of work on this 20 years ago, purely theoretical, and there were no empirical constraints 20 years ago. That's part of why I stopped working on this. And so what you do now is you say, well, this gap contributes to the pressure. The value of the gap is very uncertain, but how it contributes to the pressure is well understood. So if you mess with that whole story that I described before by adding a gap, how much of a gap do you have to add before you wreck the agreement between theory and data? And the answer turns out to be if you add a gap that's bigger than 216 MeV, you wreck the agreement between theory and data. And now you ask, Krishna, when you were doing work on this 20 years ago, what did you think the gap was? And the answer is, go back and read the papers there's hundreds of papers from 20 years ago. The estimates of the gap were around 100 MeV. we now have an empirical constraint saying it's less than 216. This is really tantalizing. This is the first empirical constraint on the properties of superconducting cold quark soup that as may be found in the centers of a heavy neutron star. And so it's a completely different way of probing quark soup, in this case cold quark soup. It's matter under pressure, which doesn't explode. But is there any other way of getting matter under pressure that doesn't explode? There's no other way of squeezing quarks to these high pressures, is there? But there is. A proton itself. And this is a setup for Fiala-Shanahan's talk in 8 weeks. Every proton in the universe is a tiny drop of quark soup. It formed in the Big Bang, 10 microseconds after the Big Bang. So what's the pressure inside a proton? That's not a question, when I was a graduate student, that's not a question I thought we would ever be able to answer. But Fiala-Shanahan answered this question, and she'll be giving the lecture in 8 weeks. And the idea, which these are 2 slides from a different talk by Fiala-Shanahan, you might see them in 8 weeks. There's an enormous pressure in the center of a proton which pushes the quarks outwards. But then those rubber bands, if the quarks stray too far out, they get pulled back in. That's like a negative pressure. And this is somebody's cartoon. This is a pencil drawing. But this is a Fiala's calculation. First principles calculation, the red is the result. Fiala will describe how this was obtained. As I said, it's something that when I first learned this subject, I would have said this will never be calculable, and it's been calculated. What's this pressure right here? It's about 6 times 10 to the 29 atmospheres, which is twice the pressure in the center of a neutron star. And remarkably, and I will say, this comparison in this bullet, I figured out on Sunday when I was preparing this talk. I've never seen this before. Anytime you give a talk, you should learn something new in preparing the talk. This is what I learned. The pressure inside a proton, which Fiala-Shanahan calculated, is very close to the pressure of hot quark soup, which I showed you at the very beginning of the talk, not at 5 trillion degrees, but at 1.5 trillion degrees, at the temperature at which it falls apart into a mist of protons. So remarkably, it is as though protons remember the high pressure soup from which they were formed. The pressure inside a proton remembers the pressure of quark soup 10 microseconds after the Big Bang when the protons were formed. They've kept this high interior pressure. So why don't protons explode? And that's the mystery of confinement. The essence of confinement is that protons don't explode. They have this enormous pressure in them, but they don't explode. QCD describes this. You saw Fiala's calculation, but I don't think it's understood in a qualitative way yet. This is the essence of confinement, and that's where I'll end. So the story that I've told you, the universe was filled with hot quark soup. Every proton formed from that soup. Heavy ion collisions reproduce little drops of it, which promptly explode. Those explosions tell us that the soup of the Big Bang and the soup in these explosions is a very, very good liquid. We are on the verge of being able to do the experiments that will be Rutherford scattering off this stuff, and at the same time will allow us to see the ripples in it when you shoot a bullet through it. Cold quark soup, well, it's at the centers of neutron stars, and it's also inside a proton. And the fact that QCD confines is the statement that QCD describes quantitatively that protons don't explode. This, to me, is the best sort of intuitive way of describing what the magic of QCD is. I only discovered it a couple days ago, and I'll end there.
All right, thank you very much for this very stimulating talk. We are under a little bit of time pressure, so let me ask for a few questions. David, did you want to?
You get to push the button.
Yep.
You're supposed to know how to push the button.
I know how to push the button, I think. So this is actually more of a very short story about Jim Simons and Rick.
Yes.
So when Rick was built, there was a big federal budget cut.
Yeah.
and it had money to be built, but not to operate. And Jim Simons thought this was ridiculous.
Yeah.
Jim at this point had just really starting to make significant money with his company. And Jim's first science philanthropy was to give Rick the money it needed
To run for that
to
one-
run for that
1 year.
That 1 year.
Yeah, it wasn't the first year, it was like the third or fourth year.
Yeah.
It was
And
completely ridiculous. You know what the consequence of that was? Do you know the, well, first of all, very important scientific discoveries were made, and that's what Jim was trying to support, and he was completely successful, and I've given you a sense of that. The US government was embarrassed by this because of what David just said. Just think about it. You're the US government, we are all taxpayers. You've built this facility and you don't have the money to run it for a year? And then some philanthropist comes in and gives a few $1 million for the electricity costs of the accelerator to run it for a year? That is embarrassing. They fired the lab director. I don't know if you knew that. The director of Brookhaven National Lab was fired because he had the temerity to accept that gift. And I'm forever grateful to both Jim Simons and to that lab director, whose name was Praveen Chowdhury. They both showed better judgment than most.
All right, so one or two other quick questions. Yes, and then.
Yeah, thank you for a very interesting talk. I think, like, as you were summarizing, going back and forth between the gluon soup and protons, we kind of straddle the boundary between few particles and many particles.
I did.
So I guess my question is, like, in what sense are we talking about explosions, soups, pressure, fluidity, or like phase diagram?
Very good. So which are you a scientist, and if so, from what field?
Kinetics matter.
Okay. So you've just hit one of the hot button questions in my field. What's the smallest droplet? What's the smallest thing you can describe with this language of a liquid and pressure and temperature and so on? That is one of the central questions right now. And I have blurred it on purpose in this talk. So when you collide two lead nuclei, absolutely many-body system, 30,000 particles in the final state, many-body system, macroscopic, for sure. These kinds of asymmetric explosions have now been seen in collisions of a proton with a lead nucleus at the LHC and a deuteron with a gold nucleus at RIC. That seems too small. People were very perturbed by the fact that you see liquid-like behavior in systems in which the final state only has 30 or 40 or 50 particles and not 30,000. But maybe we shouldn't be perturbed. But then the puzzle is that the jets in those collisions seem to be unmodified. So there is a experimental run that will happen at the LHC this July in which they will collide oxygen nuclei. Oxygen nuclei are bigger than a proton and a lot smaller than lead. We theorists have made quantitative predictions both for the asymmetric explosions and for the modification of jets. Both should be seen in oxygen collisions. If we understand what we're talking about, and if oxygen collisions make a drop of liquid, we have predictions that will be verified by the end of 2025. The idea to describe a proton as a little drop of liquid is insane. Okay. And I did it for you anyway. That's insane. And I did it for you anyway because I felt like it. You're not going to hold me to it. But it's insane. And so I was really shocked when I looked up. So Fiala computes the pressure. I look up and I compare it, and it's the same. So maybe that insanity is not so insane, but it's insane. It's on the edge of violating what you know.
All right, so one last question. Can you use your seat mic so that people can hear you?
Oh.
Yeah.
I guess.
Yeah.
Okay.
Please.
Sorry. Thank you, Professor, for enlightening us. It was a most fascinating lecture, and I'm so lucky to be here.
So come again in 4 weeks and in 8 weeks. I've tried to set up.
I will,
my two
believe
colleagues.
me,
So And Fiala is my colleague at MIT, so I actually spoke with her. I have a sense. Anna Watts from Amsterdam, I didn't check with, but she's going to speak about neutron stars, so I've set her up too. I didn't speak with her in preparation. But come in 4 weeks and 8 weeks, and please go ahead.
I look forward to those evenings. Yes. What I remember being enchanted by the name. The first time I heard of a quark, I heard of one called Charming,
Yes.
and I was just
You want to know where the name comes from?
no. I want to know what is your favorite quark name.
Well, charm is better than bottom and top, which are the heavier ones. The names are up, down, strange, charm, bottom, top. So you picked a good name to highlight. I will say they had to be called something, and people in the 1960s, and well, for bottom and top 70s, came up with these names. Strange, actually, you could understand, because the first description involved ups and downs, and then you started to see something strange, and people introduced a third quark in their bookkeeping, and they called it strange. You can understand that. I have no idea why the fourth one was called charm. I don't actually know. But charm quarks are actually a lovely part of this story that I didn't tell. How do we know that quarks in the soup can diffuse around and travel great distances? Well, travel a fair distance from where they were produced in the soup. We actually know that by studying charm quarks in the soup. I didn't have time to talk about it, but I said that this stuff is, the quarks are not confined, they can travel around, but they travel around always bumping into each other. How do we know they travel around considerable distances? It's actually by looking at the physics of charm quarks in the soup, and I could explain that to you afterwards. So charm quarks, in addition to having a nice name which has no meaning, do play an important role in the story that I didn't have time to tell.